Let me comment on the name of this technique. I've abandoned the 4 Russians technique as a name because it's a terrible othering term. It was, I mean, there's an original paper in Russian by these 4 authors, Aglatsarov, Dinitz, Gronrod, and Parachev, probably butchering the pronunciation. They all worked in Moscow in different institutions at the time, so clearly they were all Soviet nationality at the time. Gronrod never lived to see the what we today call Russia again, so who knows if it's appropriate to call him Russian. Dinitz emigrated to Israel and now has Israeli citizenship, as far as I know. So it's at least borderline today, and I mean it's just not a great term. It very much sounds like Iron Curtain. It's in widespread use, so you should know what is meant by the name, but I will use something that's much more telling because exhaustive tabulation is what this really is about. And we could do it the same kind of disfavor in forgetting who invented it as we do for other computer sciencey techniques. Where the advantage is that we give it a name that tells us what it is, not who might have invented it. The joke in math is things are always named by someone who invented it the second time or so. So even giving credit is nice, but giving credit inappropriately or incorrectly is maybe less nice than just calling it by some name that reflects the content. Anyways, so here in kind of a bit more cleaner write-up, the same application, which is, I should say, is not exactly what they initially thought about. It's not the way they framed the technique. Indeed, they get a slightly better speed up at the time, but the way I'm presenting it here generalizes to other problems. So I think this is closer to the essence of what we now today see as the exhaustive tabulation technique, even though it's not historically how they first thought about it. I don't know, maybe in hindsight, you appreciate this more. I can maybe sketch at the end what they originally did. I want to also use this name here because we'll reuse that. Where, again, think of multiplying matrices. That they're Boolean is not even so important. They could also have values from another very small universe. The point is it has to be a small discrete universe, not some unbounded or even real numbers, something like this has to be small discrete. And there's some way to define what multiplication and addition do, and we're not very fuzzy about the details of what these operations are. In particular, you can do it for min plus multiplication as well as for the more standard Boolean multiplication. Okay, long story short, you divide all the matrices into L by L square sub-micromatrices. Then clearly all the matrices consist of that many micromatrices, n over L squared. And each entry in the result you get from summing up n over L little products. That's what we had last time as well. The number of possible different pairs of micromatrices really is this number. Right? You have 2 entries for each of the L squared cells in the micromatrix, and you have 2 of these, so you take the product. That feels like a lot, but it's not a lot if L is sufficiently small. That'll be the point. In particular, if you use square root log n with an appropriate factor, one quarter is enough, then you get precisely the square root n different combinations of pairs of micromatrices. And since that is not so much compared to the input size, you can afford to compute all of those that could possibly arrive, whether or not they occur in your matrix. And we can do this for whatever operation is convenient. Here, we really don't care, and we'll just have separate tables for multiplication and for addition. Right? It's completely oblivious to this definition of the matrix multiplication. Then if you look at so how we arrange this table of results, also you have flexibility, but one option is you just list all the entries of the 2 matrices, one after the other, and you treat the entire bit string of all the entries as one giant, or maybe not so giant, binary number. And because it's a number, you can use it as an index in an array. And so with a single memory access, you can read off the result of these micromatrix operations after the pre-computation. And the pre-processing, you can also work out, like depending how expensive the pre-processing is. Maybe it's at most cubic, and then the size of the L cubed works out to log to the 3/2, and you have so many of these. Okay. Now the total time to compute one entry in the result is summing up n over L of these micromatrix products, right? You could do the summing up in constant time each because we pre-computed the sums as well, just because we could. And so the total time is n over L for each output cell. N over L squared output cells makes n over L cubed in total. And so you get this, the total time n cubed divided log to the 3/2. And the original variant of the 4 Russian authors, or not of Soviet authors, they divided the two matrices into very thin or wide very thin or tall strips instead of little squares. And then you can work out that there's you're essentially decomposing the result matrix into a sum of low rank matrices, and you can compute all possible low rank matrices the way you need them in an efficient way. So you're using the same trick, that there's only a certain number of possible ways that you have to compute these, and you can just brute force those. That has the benefit, you only have one L in this formula, so you can make L substantially bigger, square of what we had, and so you get a slightly better speed up in the end. They can't do the summing, they have to do trivially, so they don't get the third power of L here, but they have a larger L, and so here this works out as the better result. The way I present it here is not to convince you how to do matrix multiplication, but to teach the technique that will apply to our string alignments. And there it's a bit easier if you work with these squares. How can we apply this to edit distance? We have as output a matrix, so clearly there's some superficial similarity, and we can divide the output matrix, our L, in some submatrices, micromatrices, L times L. The way the alignment matrix, or the dynamic programming matrix, is set up, these correspond to two substrings of the strings that we align. And now you have to study a bit deeper what the problem is about. And here I took the figure from Dan Gusfield's book, where this is also explained in more detail than I'll talk about if you want to read it up. There's different parts in the matrix. There's the top left corner, which plays a somewhat special role. Then there's this first row and first column. And of course, there's the string, the substring that corresponds to this cell. And the claim is that you can compute all the values in F, which, if L is not very tiny, here L is 4, so it's a small example. But if L is a little bit bigger than that, F is the majority of the matrix. It's the big part of the matrix. And you can compute all the values in F just from these A, B, C, D, E. Why is that useful? Well, we can, again, apply exhaustive tabulation to all those entries. A, B, C, these are not too many numbers, roughly L numbers, 2 L numbers. And then there's some letters from the strings. If we make L sufficiently small, there shouldn't be too many possibilities how these can look like. And so you could pre-compute filling much of the matrix in the same way we've done this for Boolean matrix multiplication. There's a few catches, though, in that if you think about the typical edit distance matrix, it tends to start with zeros, and then the numbers progressively become bigger. And at the end, in the bottom right corner, you have the final edit distance of the strings, which might be up to n, right? We hope that it's a bit smaller, otherwise the alignment is useless, but it might be large numbers. it's certainly not just 0 or 1s. It's certainly not just a bounded range. It grows with the input size. Anyways, in the worst case, it does. So this doesn't seem to work. How can we apply this exhaustive tabulation here? And the trick is the numbers do grow, but in a way, they grow in a very predictable fashion, and they can't grow by all that much. They don't jump. You usually do an increment by 1. Maybe you leave something the same, but that's about it. So in a way, we want to use a difference encoding, and then things are back to a nicer small range. In the recursion, you never decrement a value, but you do the minimum from different places. So if you carefully study this, if you look at a certain cell and its neighbors, so here's ij, then you might go to the next row or column, and also the diagonal one. So these are the differences that we look at. Each of these cells takes that upper left one as one of its minimum possibilities, as one of its entries in the minimum of 3. And so clearly these cells will not be much bigger than the top left cell. That's the trivial part. The difference cannot be more than 1, but it can also be -1 in cases where the minimum comes from the outside of this little figure. So if this cell takes its minimum from above or from here, then you can work out that it might end up being 1 smaller than the left neighbor. Basically, if you have some value x here, what's the worst it can happen? This can be the same for edit distance. This could be x plus 1, right? Then you have your distance 1. That's one case, and you have to study the others. In principle, it could go up and down, could go up for a long time, and then at some point you branch off. But you can show you never differ by more than this plus minus 1. So if you apply conceptually the operation to the differences, not the matrix entries in absolute terms, then we can still use this exhaustive tabulation. One way to do it that is, again, optimizing a few things a little bit further is that you leave out this top leftmost cell, essentially give that an offset of 0. And now each of the cells here, these are input cells that you have to specify. Same with this. Let me maybe mark this. These are cells that are input to the micro operation. And these are outputs for the micro operation. Each of these cells you have to read as a difference to the left neighbor. Right? This cell could be substantially bigger than the left top corner. But if you want to know its value, you have to add 1, subtract 1, do nothing, add 1. So it's 1 bigger in this case. Okay. These you fill essentially from the recurrence that comes recursively back to you. And now the micro operation has to fill the light green part. And that is all determined from the numbers that you have. And maybe the string as well. Although you can also, like in this more recent paper, they tried to get the dependence on the string minimal. The number of different micro matrices, if you include the string in the simple version, is 2 strings of length L each. So if you have sigma characters, that's sigma to 2L different possibilities of things that you could have written on top of the matrix. And the entries in the top and left first row, first column, they can be one of 3 things each, plus 1, 1, minus 1, plus 1, 0, minus 1, and we have 2L minus 1 of those. So here, if we want, again, the number of different micro matrices that we have to do the exhaustive tabulation for to be reasonably small, say root n, we have to pick a fairly small L. In particular, the log here is involving the alphabet size. So even if we set sigma to 4, that's already taking log base 12. So if you think about it, that's essentially the length of a decimal number, right? So you want to be in the millions before this makes any sense. So in practical speedup terms, you have to work on this more, and people have tried to reduce the size here a bit more. But in theory, like if you look just at the asymptotic scale up and pretend that sigma is a small constant, it helps a bit. So in particular, you can choose L to be essentially a logarithmic. You have n over L squared micromatrices to fill. By the way, in each case, you're never filling these middle values in the recursion, at least not until you have to. And you can work your way around to never do it. Filling the table this way gives you the bottom right corner, which is the answer, the final edit distance. And for the backtrace, you can also involve micro matrix operations if you want to. Okay. The only thing you fill is this grid of this sparse grid of rows and columns, which gives you enough information for the next cell to feed into. So overall time under these assumptions are improved a good bit. You essentially get the two logarithmic factors speed up. One from filling fewer numbers. The number of things you fill in the cell goes down by this logarithmic factor. And you're also speeding up the computation in the micromatrices by doing table lookup. It becomes constant time, what used to be size or linear in the size of the submatrix. Okay, so that's the positive part. Now, I said I started this section asking, can we do better? Is there something inherently quadratic about edit distance? And it seems so. This is all fairly recent developments compared to other parts of complexity theory. This is from an area called conditional lower bounds or fine-grained complexity theory, where you try to use NP-hardness-like reductions to prove lower bounds for polynomial time algorithms. And in this case, the result you can prove is that any edit distance algorithm for two strings of length n that would take a strictly, so for, well, n to the 2 minus delta time, but delta has to be a constant. So our logarithmic scalar speedup does not qualify for this. If you had such an algorithm, you would refute the strong exponential time hypothesis, which is listed down below. I'll briefly comment on it. But for this module, I guess you can pretend it's a somewhat widely believed complexity theoretic assumption. So we don't have strong evidence in either direction if you're very strict, but a lot of people are building things on top of Seth, the strong exponential time hypothesis. And nobody has refuted it. So it seems reasonable to assume that this stronger running time for edit distance is not possible. So people often call this strictly subquadratic, or sorry, was there a better term? Truly subquadratic, something like this. It's not very well defined, but what we mean is the exponent should be strictly less than 2. The exponential time hypothesis is something that popped up in advanced algorithms, where it says I can essentially not solve 3-sat in sub-exponential time, but I might be able to squeeze the exponent or the basis of the exponent to some smaller constant than 2. Who knows? You should compare this to the easy brute force algorithm for 3-sat, where you just guess an assignment, and that there are 2 to the n assignments or 2 to the k for the number of variables. So that's easily doable. The exponential time hypothesis says maybe you can lower the exponential growth by some constant factor, but you need exponential. And this is, I think, very widely believed. It's stronger than assuming p not equals np, but still there's good support for this in terms of the number of people that speak up for it, whatever that says. The strong exponential time hypothesis makes this assumption a bit more quantitative and a bit more strict, or a bit more strong, hence the name. Here you look at the generalization of 3-sat, where the literals have k literals, sorry, the clauses have k literals each, not just 3 as in 3-sat. And then it says, whenever you pick some epsilon by which you want to improve the exponential basis, then there is a size for the literals where you'll fail, where the k-sat problem needs at least, well, the stated bound. You can't reduce the exponential basis arbitrarily much if you're willing to look into larger and larger clauses. And so that's the thing that the statement here is based on. Again, all the algorithms we know respect this, so we have no reason to believe it's false. So in a way, we have a lower bound that says we can't reduce the exponent strictly by anything that is constant. And we have an upper bound that says, yeah, we can shave off logarithmic factors. And for a whole class of problems, that's the kind of state of the art. Okay, so edit distance is one of these. Unlikely that we'll see subquadratic algorithms in the strict sense. That's maybe worth mentioning that this reduction even works if the alphabet is constant. So it falls in this range where we do get this logarithmic speed up from the exhaustive tabulation technique.